they are slightly more, and perhaps it's sort of opening up to new sub-science within hydrology and meteorology. So next is to repeat just briefly my introduction last webinar, why uncertainty is an issue today when now the models are much better than 20, 30 years ago. And of course, the reason is that now we are so good that people start to take our forecast seriously. And also the challenge is to address the problem with extreme weather. And there is also the competition or emergence of over-detailed deterministic weather forecasts, which of course are changing from one run to the other. People might ask, what can we trust? But also very interestingly, there's in what I would say worldwide change in the attitude to uncertainty. There are many problems outside meteorology and hydrology dealing with the decision making under uncertainty. But coming back to our sciences, what is the role of the forecaster? Is it just to communicate model output in a pedagogical way? And I mean, it's not, because first of all, the receiver must trust the communicator. And he does that if the communicator is not just a good pedagogue, but can also, for example, adapt to changing circumstances. As we know, there is not one computer, but many computers and many systems, and they might disagree, and someone has to make a choice or make a synthesis of this information. Secondly, it's also deterministic information like forecast or observations, which of course necessarily must be taken into account in one way or the other when the uncertainty is estimated. And also, as we know, making decisions under uncertainty in any field is not trivial. So the forecaster might also be asked to help the client to decide what shall I do. So there are some mathematical and psychological traps that make this uncertainty estimation difficult. And last time I mentioned a lot of interesting books, only one of which is from our sciences, Keith Bevan's latest book, but also all the other books actually interface our sciences very much, because you can more or less translate many of the conclusions into hydrology or meteorology. And one idea from these books, I think it's in Kahneman's, is about our two ways of thinking, system 1 and system 2. Fast thinking is the operational in a rush, where there is time constraints, limited information, misleading information, distraction, and still good work has to be done by highly educated experts. On the other hand, we have the slow thinking, system 2, more or less the same people or their colleagues in conferences with almost unlimited time and a wide range of reliable information and full concentration. And the problem is, in my view, and has long been, to make a transition from the sort of scientific wisdom. How can that be made into useful operational practices? And that's not trivial, because you have to make compromises considering the time constraints, etc., in operational busy forecasting. And so I put up 5 points in a sort of a program, and each point, of course, has a lot of subsections, of which I can only address a few in this webinar. The first one is to combat overconfidence. The second one is not to underestimate randomness. It's much more powerful than you would imagine, perhaps. Then all the problems estimating uncertainty, and that will be the main emphasis in my talk today. Then how to communicate uncertainty, that is also where we now not leave meteorology and hydrology, but interface strongly with other fields of social life, because there is a lot of details how this can be done or how it should not be done. And finally, and that's the same with the decision making, how to make wise decisions in your own interest under uncertainty. And now, point by point, overconfidence. And I think one tragic example of overconfidence is plane crash with the Concorde that in 5 or 10 seconds changed from being the most safe airplane in the world to become the world's most unsafe. And the reason for this particular is also the reason for a lot of overconfidence, and that is conclusions are drawn from too small samples. In this case, the flight hours of the Concorde compared to other carriers. There's also what is called the representativity error. That is confusing what is typical with what is probable. And I will not go into that, but concentrate on the confirmation bias. That is a human habit of looking for arguments that support our views and not so eagerly looking for those that might contradict. And then I will not go into this, but there are psychological or social mechanisms. Perhaps you want to impose your will by appearing very self-assured. On the other hand, there might be outside pressure that you should be confident, and that often means that people want you to make the decisions for them. But I will concentrate on the confirmation bias. And here is a typical forecast overconfidence statistics. It happens to be, it's rather schematic, but it's more or less typical for rain forecasting, more or less as it has always been in meteorology and perhaps also in hydrology. That is that the forecast probability is the x-axis, and the observed frequency on condition on this probability is on the y-axis. And in a perfect world, all these green balls would be along the 45-degree line. But as you might not be completely unfamiliar with, when we forecast it will absolutely not rain, still it tends to rain on a fraction of time, but still it's not perfect. In the same way, when you promise that it shall rain, then it perhaps only occurs 70% of the time, and then interpolating in between, it means that we over forecast, or we are too confident about the probabilities in this type of rain. But as far as I understand, it is also true for tests where people are asked about the capitals of different countries and have to assess how sure they are that they are right. And also so that people tend to be too confident about that they are right. But in our profession, forecasting, perhaps this sort of schematic mathematical diagram serves as a good introduction. We have in our back of our minds some sort of climatological know-how, how it usually is, with the climate average and then a spread around this climatological average. That is how it sort of usually is. Then we have a preliminary forecast. That might either be our colleague working before us has made a decision about the likelihood of something. It might be a computer-generated forecast or something else that we have to take a stand on. And then there is input from outside. And one input is perhaps new observations and forecast, perhaps a deterministic forecast. And then we have to modify, and that might be a matter of minutes or half an hour to modify our first preliminary forecast into something that takes this new information into respect in one way or the other. So this is a schematic illustration of the forecasting process. And in the end, we come up with sort of the most likely value and the uncertainty around that value. The confirmation bias I put up a little scenario here from a forecast office. One, I think it is the one I would apply. The senior forecaster said rain is less likely because the ensemble forecast only forecast 30% likelihood. But then somebody points out that the last NWP from our favorite model has forecasted rain. And then the senior forecaster, well, considering that it's just one forecast and the ensemble has 20, 30 or 50 members, it's not that heavyweight, but I'll upgrade the risk to 35–40%. Sort of adjustment in light of later information. Then there is scenario 2. And then the senior forecaster has first seen the NWP, and it has rain. It is his favorite model, and he's very confident. I'm 80–90% certain there will be rain. But then his assistant points out that the ensemble only gives 30% probability of rain. And then the psychological mechanisms might work in a way that the senior forecaster says, well, let's reduce 80–90 to 70%. The point here is that presented with the same type of information but in differing order might lead up to different final assessments of the risk. And this is one example of the confirmation bias. It could also be of what is called the primacy bias, because we know from other studies that the order in which information is presented actually affects the decision making, also outside hydrology and meteorology. And it might also have an element of the anchoring effect, but I skipped that and go on to a case which sort of shows another fallacy of overly confident and detailed forecasting, and there is no real reason to be that detailed and confident. It's on a real case in Sweden in summer 2004, and it turned out to be heavy flooding in this part of Sweden. And the meteorological service 4 days in advance warned about 40 millimeter, more or less in the same place. It was based on the slavish interpretation of the European Center forecast. Next day, however, this determinative forecast had put the main rain to the northwest. So now this area was warned about heavy rain. And 2 days before the event, it was in the other extreme, in the close to the bay, to the Botnian Sea, to the OC, and it was a bit jumpy. And only 1 day before did the forecasters return to the first forecast, forecasting more or less correctly 50 millimeter in the right place. Now, this might look like two good forecasts and two bad forecasts, but since all this jumpiness made people confused and nobody really could trust any of these forecasts, they were pretty useless, all of them, but they couldn't be a base for any clever decision. The hydrological, the sense moral of this is that details and high confidence is fine if they verify. And that is something to think about in our days when the high resolution models look very detailed and confident. But how much can we trust the very details? Now this was in 2004, and we had then also a hydrological forecast service working semi-independently of the meteorologist. And they started 4 days in advance to say that somewhere in southern Sweden there will be 30 millimeter. They didn't pretend to make any details. Somewhere in southern Sweden, and that is what they could stand for. The next day, more or less the same forecast was repeated. Somewhere in southern Sweden, perhaps except the most extreme southern parts, there would be a risk of 30 millimeter. 2 days, they narrowed in to central parts of southern Sweden, and 1 day in advance, more or less the same forecast as the meteorologist, more or less spot on where the rain was due to fall in 1 day's time. Now, in this case, they didn't promise more than they could deliver, and the consequence was that a lot of people, of course, were alerted for the first day, but were then gradually left out from the picture. And the point is that these people got confidence in the forecast because they could see how the forecast narrowed in to the spot where the rain would fall. So this type of forecasting had an effect on the decision making which was not possible with the methodological version. So the sense is that we should not promise more than we can deliver to uphold the trust from our customers or the public. Now the point 2 is the problem with randomness, where we have a tendency to see patterns in completely random patterns or time series. And again, the notorious error is drawing conclusions from too small samples. Then there is an interesting statistical effect that is, I think, more interesting to climate scientists, because by running means, you might actually induce spurious periodicities that do not exist in the original data. But I will concentrate on the lethal, deadly regression to the mean effect, which also fools us to think that we have found a message when there actually is none. I was on a conference in Reading 1.5 months ago, and at least 2 presentations of the work that had been taken 1 or 2 years actually were completely meaningless, because what the scientists have found was regression to the mean effect that gave spurious results of the new value. So it's really something to look out for. Now, this is one example. When I worked at a European center, we got constant feedback from the member states, which was very good and very interesting. And one of the comment was that they had discovered biases or model drifts in the center's model. And here's one example which I can publish because it has already been published at a user meeting in 2011 from Meteo France, who looked at the mean error over 15 days forecast. And there's an initial bias of 0.5 degree, but after some post-processing, it's more or less non-biased the first 4 or 5 days. But then the model seemed to drift rather abruptly down to a bias of 1.5 or 2 degrees. And if this is the case, then it's a real serious deficiency with the ECNWF model if it tries to forecast monthly or seasonally. So did this had any substance? And indeed it had not. It was actually a very good example of the regression to the mean effect, which I will show how that works. Here we have some sort of abstract space with the climate, and then we have some verifying state not too far away from the climate. And the forecast made, 1-day forecast, 2-day forecast, end up not far away from the verification as we can imagine. But with increase in lead time, forecasts tend to, of course, be more distant from the verification. But still, they cluster randomly around the verification. Then for longer forecast, the distance increases. And for forecast, let's say, beyond 10 days, there's a very low skill. And when it's very low skill, as we all know, a climate guess is as good as a forecast. So this forecast beyond 10 days more or less scatter randomly around the climate. That is a well-known fact. So skillful forecasts cluster around the verifying analysis, and longer forecasts with less skill tend to cluster around the climate average. Now, what happens now if we are in a persistent anomalous situation? So let's say constantly warmer than normal. So now the verifying analysis and the initial state is far away from the climate. Still, a good model is able to pinpoint, as before, forecast close to the verifying analysis. However, for the longer forecast, beyond 10 days, they cluster around the climate. And not because of any systematic error, but just because they are not very skillful. So this means that there is a transition from skillful forecast to non-skillful forecast. That is, of course, the effect of non-systematic errors, making the point of gravity slowly shift from the anomalous state to a climate average state, which in this case means it looks like there is a model drift, which is not the case. And in this case with the Météo France verification for February 2011, it was indeed 1 to 2 degrees warmer than normal in France. So what we saw initially was just an inability of longer forecast to skillfully forecast the persistence of this anomaly, not any model drift in the normal meaning. Then the main part of the 5-point program, and that is to estimate uncertainties. And of course, there are a lot of objective schemes doing that, but in the end, they will be presented, modified by operational forecasters to be of the best value. And there are a lot of statistical or psychological traps, and one is a halo effect. And that is, for example, that everyone has our favorite model, depending on from what continent you come or from what country you have your favorite model. And that might unduly affect your appreciation or how much you weight that particular model in combination with other models. Then you have the primacy effect, as I mentioned before. We know from other investigations that the order in which information is presented has an unwanted effect on how much we appreciate different types of information. Then the representativity effect, which is also well covered in the literature. It means essentially that we confuse what is typical with what is probable, and that leads to also misrepresentations. Then the availability effect is affecting how easily we get access to different types of information. So if one model is very well presented, another model is less well presented, of course does not affect or should not affect our appreciation of the skill. But of course it will have an effect on how much we trust. And I remember from the time when I verified manual thunderstorm forecast, the 24-hour thunderstorm forecast made in the afternoon were better than the 12-hour forecast of thunderstorms made in the morning. You would expect that the shorter forecast is better than the longer forecast. But the point here is that when the 24-hour forecast of thunderstorms were made in the afternoon, the forecaster had on his map, on the radar, a lot of indications of thunderstorms. So they were more available than in the morning when he might have none of them, and perhaps instead he had some haze or even fog, which was not sort of inspiring any thoughts about thunderstorms. So I will leave that and take up again the regression to the mean effect, and then the problem of combining probabilities, and the deceptive inconsistency or consistency, and then also the effects of correlations, which we will meet in our job. And the regression to the mean in forecast is illustrated by this ECNWF epsogram from last summer or the summer 2012 from Barcelona, where you can see first an initial heating up to 35 or 37 degrees, and then a slow cooling down to 27, 28 degrees at the daytime. So with some increasing uncertainty. Now to put that into some focus or in some context, the European Centre has, and to show that it is that there is a strong element of regression to the mean in this cooling, the European Centre has also an option where you can look at the model climate. And the idea is that what is anomalous in the forecast to the model climate might also be anomalous in the real atmosphere. So here we can see how the same forecast now is clearly anomalous around Tuesday and Wednesday, the 21st and 22nd, and then slowly drifts towards the climate average, and also the spread increases, more or less covering the spread in the climatological database from several model runs which have been used to build up this model climate. So here is a practical example of how the regression to the mean effect looks as if there is a cooling, which in some sense there is, but it's actually a return to the average. And to further clarify, I have here a schematic image of the epsograms from day 3 to day 12 of some weather. It could be temperature, it can be rainfall. Anyhow, you will see some sort of evolution. The median will rise and fall and show some variation. And to further assess this, we can look at the spread. The spread is, as we can expect, slowly increasing in this forecast. If we now look at the model climate projected behind, we can, for each of these boxes, draw some conclusions. The first one is anomalous. It's away from the climate, and it has a small spread. So this is clearly a forecast signal. There is some value in this forecast. The next one has the climate value. It also agrees with the climatological value, which of course can happen, but since the spread is very small, this means that this has also a forecast value that it can be used for decision making. The third one has large spread, very large spread, very large uncertainty, but it's also quite deviating from the climate. So there is an uncertain signal, but it more or less says it will be quite below the climatological average. And that means there is a forecast signal, there is some information to draw from also this forecast range. However, the last one again has the median or the mean at the climatological average, and the spread is more or less identical to the climate spread. So this means that this forecast more or less tells us, I don't know, I have nothing to contribute, I am not more certain than a climatological average. So here there is no forecast signal, no forecast information apart from the climate. Then also the variations here, it's good to keep in mind that at the beginning of the ensemble forecast, the variations are mainly of sort of atmospheric processes, advection of cold air, warm air, what we are well used to. However, at the later stages, it's mainly a statistical effect of the regression to the mean. So it's a gradual change from dynamical processes to statistical effects, even if the curves might look quite similar. Then consistency is, of course, something good. Everybody wants to be consistent, so it has a positive value. But it can also be easily misunderstood. And here is now a schematic illustration of consecutive forecast from the same model, valid at the same time. So the first one was dry, and then it was forecasting rain and rain in 12 and 24 hours later runs. So it's rather consistent, at least the last two forecasts. So it's rather consistent. In contrast to this one, which starts with the rain and then it flip-flops to dry and then back to rain. And this most of us would deem rather inconsistent. However, I found this when I worked at the Met Office, and then I confirmed when I came to the European Centre that statistically, when you look at what actually happens, rain is more likely in the last case with a jumpy forecast and less likely or slightly less likely when you have this sort of consistency, which is sort of completely counterintuitive because we would trust the first forecast sequence more to give rain than the last one. But that might be because we are applying our moral beliefs in how humans react on the computer and the mathematics, but it does not necessarily apply. The explanation to this, I think, lies in the role that mutual correlations play. So here are three balls, and they are proportional to their perceived hit rate. So the shortest forecast has the largest hit rate, and the 60-hour forecast has the smallest hit rate. Also, when there is no rain forecasted, of course, there will be some rain, so that circle is also part of the bag. So, but now since the 36-hour forecast and the 48-hour forecast are just 12 hours apart, they are, as we know from our knowledge about data assimilation, where you have a first guess depending on the previous analysis, more or less modified by new observations, but not completely changed. It means there is some sort of surviving correlation between successive forecasts. So these two forecasts, the 36-hour and the 48, overlap in some mathematical sense quite a lot, whereas the 36 and the 60-hour forecast overlap less. So if you then regard the total green area as a hit rate of the whole system, it might be that the 36 and 60 hour, because of their lower correlation, is slightly more skillful than two consecutive forecasts which are correlated. So this might explain why this sort of jumpiness is not as bad as we would imagine from our normal moral standards. Something similar explains also when we want to combine forecasts. So here there are three different models, and two are slightly better than the last one, NWP2. But two of NWP1A and NWP1B are very correlated. Like, for example, if we are talking about the ECWF's operation model compared to the EPS control, more or less the same model, just in different resolutions. They are both good, but also highly correlated. That means that a slightly inferior model would actually serve better to be combined than these two rather correlated models. So the problem of combining different models is not only a matter of how good they are, but also how similar, how mutually correlated they are to actually provide added value. And then finally, and this is perhaps a bit complicated, but I try to make it as easy as possible. When I worked at the European Centre, I often got the question if we could add the probabilities given from the EPS, for example, in the EPS grants. And my answer was that it generally is not possible, and I will explain why. So here we have an example of 30% risk of rain in the morning and 40% in the afternoon. And the problem is, can we say something about the risk of rain for the whole day, a 12-hour period? And if we get this information from an ensemble, the only safe way is to actually go into the data, if it's possible, and count the number of members who have rain in both periods or in either of the two periods, so we get the total risk of rain for the whole day. There are still some special cases when one can make a shortcut. And that is when the rainfall is highly correlated or anti-correlated. Then I change from the y-axis having the number of members to a percentage. So in a case where rain in the first period is followed by rain in the second period, plus some more rain, then the total risk is 40%. Or anti-correlated, that rain in the first means dry in the second period, dry in the first means rain, or rain in the second means dry in the first. Then we can add these two and get a total risk of 70%. But these are very special cases, and in the rest, and that would be 99 or more % of the cases, this formula applies that rain at any time during the day, in this case, is the sum of the probability in the morning plus the probability in the evening minus the probability of having rain in both periods, both in the morning and in the afternoon. And this equation can be understood if in the next diagram we have the equation at the top, and to the left is the laborious work of just counting the EPS members, and to the center and the right I have introduced, which I think is a very good instrument to understand probabilities in different ways, and that is called the Venn diagrams. So what you have here are two imagined distributions of rain in the first period, depicted by a smaller circle, and rain in the second period, a slightly larger circle, more or less overlapping. Or you have some more boxes with straight lines doing the same job. So this type of the graphical display explains also the reason behind this equation above. But I leave that for your extra interest and go to the fourth point, how to communicate uncertainty. And it can be done in numbers, words, graphics, or intervals. And the point is that the message is understood. So it's very much dependent on who you are talking to. Interestingly, the Bank of Sweden, I discovered last week, have, I think, inspired by the Bank of England, which in its turn in 2005 started a dialogue with the Met Office about how to display economic or financial forecast. They've introduced more or less the ECWF plume diagram for the economic forecast. So here is now the Bank of Sweden's forecast of the gross domestic product for the coming 6 years. And as you can see, it's a large uncertainty. What I will concentrate on is what is called the framing, the base rate, and then the problem with 50%. It's also an interesting case with total uncertainty when you are completely lost. That was actually what I discussed in the previous webinar. So the framing effect is, and this is not what I have made up myself. It's actually some of these books that ask people about tested their understanding of probabilities, and it turned out that 30% risk of rain was less understood than 70% chance of dry weather, although they of course express identical messages. So it reminds us of the famous bottle that can be both half empty and half full. So, but I can't say which one of, if we should stop talking about risk of rain and instead chance of dry weather. But objectively, there is a difference in people's understanding, which I think has to be explored further. What I know is that the Met Office experienced some years ago that when they made individual probability forecasts for severe thunderstorms for individual locations, and then of course the probabilities for severe thunderstorms were typically 10 to 20%. The authorities in these cities did not act how you would expect. Only when they changed the frames and say 60% for the whole region, in this case the Midlands, did the authorities act in a sort of reasonable or logical way. Although the number is mathematically equivalent to these smaller numbers for individual locations. Then the base rate, and people often forget about the base rate. And personally, I made that error in London when I heard people speak Portuguese in London, and I assumed they were from Portugal, but they were from Brazil, because there are 10, 20 times more Brazilians in the world than Portuguese. So that is how the base rate can affect you in normal life. But probability statements can be better understood by reference to the base state, and the base state in our science is climatology. And one nice example of this application is the extreme forecast index from the ECWF, which is the 5-day forecast valid just now, and it shows the how much the probability of the 2-meter temperature differs from the climatological probability, pointing out regions where it's unusually warm colors, or unusually cold, green and blue. So this is another way to highlight probabilities in an efficient way. Then there's a universal problem with 50%, and there are some meteorologists who never issue a 50% probability forecast because that is misunderstood, as they don't know anything. But tossing a coin, then 50% or 50-50 means I don't know, because the base rate is 50% for a coin. However, if you tell people in Barcelona it's 50% of risk of snowfall, of course that is a very strong message and a high risk, and I think will be taken seriously. Also, if you said that there's a 50% of sunshine in Barcelona, it's a relatively low value compared to the climatological chance of having sunshine. So the meaning of 50% depends on the base rate, and we must try to convince people that 50% is in most cases informative value. The Met Office has spent a lot of time to make their warning system more efficient, and has not just stayed with probabilities, but also the impact of different weather elements. And here is how they normally warn. They grade the forecast into the probability and then the impact, and then they get a sort of combination of these two into a color that the cooler, the less dangerous, the warmer the color, the more dangerous, and that action should be taken by the public. And you can see that on their website, how it applies for individual weather situations. So it's another way to make people to communicate your warnings in an efficient way. And then finally, how to make decisions from uncertainty information. And the picture here is actually an authentic, slightly edited, but authentic image of President Obama watching the strike probability map for the storm that hit New York some years ago. So there is a lot of issues here, how to interpret, how to make decisions from uncertainties. But I will be brief here and just point out the difference between our simple cost-loss model and the next stage of complexity, the prospect model. And it's quite easy to make that distinction between if you were given this choice of either 80% chance of winning 1,000 euros or to get 700 euros directly in your hand. Then, according to the cost-loss model, where the expected gain in the first alternative is 800 euros, you would choose that, and not the second one, which is €1 cheaper. But I think everybody, including a professor in mathematical statistics, would take the 700. And this shows that the cost-loss model is sort of a good start, but just a start, and the reality is more complex. The cost-loss model assumes that the more we gain, the happier we are, and the more we lose, the unhappier we are. So there's a straight relationship, a linear relationship between our pleasure or pain and loss and gain. But according to our experiences, and that is, I think, what Daniel Kahneman got his Nobel Prize for, among other things, was that the curve is actually not linear. And it has at least two characteristics. One is that the negative is steeper than the positive. So we rather prefer to avoid a loss. We rather prefer to avoid a loss than to make a corresponding gain. So that's the first difference. And then also tests have shown that, for example, if people have the choice to choose between 100 euros for sure or 50% chance of getting 200, they would opt for the sure 100 euros rather than betting on a larger gain. On the other hand, if they had the choice between losing 100 euros for sure or 50% chance of losing nothing compared to losing 200, most people actually, perhaps surprising, actually rather prefer to bet on that, to have a chance of avoiding this painful loss. Now, this might be debated if this is realistic or not, but it shows that the decision making is slightly more, or perhaps very much more complicated than our simple cost-loss model has made us believe. And it's good that we know this so we understand why people appreciate or don't appreciate our forecast. So to sum up in the final slide, we must combat our tendency of overconfidence, and in particular watch out for our confirmation bias, and also learn to avoid seeing regularities in complete randomness. And I particularly warn you for the regression to the mean effect in this context. Then there are all kinds of mental, psychological, statistical traps that will make the uncertainty estimations biased or misleading, and we must be on the lookout for these. Then a communication of probabilities and uncertainty can be done in many ways, but the ones that actually work depend on who we are addressing. So I can't favor any specific recipe. Just to remind you about the importance of framing a base rate and not to avoid 50-50 as still being an informative value. And finally, we must be prepared to help people making decisions from our forecast. They might have an intuitive feeling for penalty functions, but I think that being good at that, we will show our value also by helping people to make decisions in their own interest. That's all. Thank you.
Well, thank you very much, Anders, for a very, very interesting presentation. And it's a lot of material as well to take in. If anybody has any questions, so please ask them now. You can unmute yourself and ask the question. Peter, you have a question?
Yes, thank you. On page or slide 12, when Anders was talking about the hydrological, meteorological forecast communication. Yeah.
Well, it takes a long time to go back to 12, but I have a paper here. So yes, slide 12. Yes.
Don't worry, just flick back. I think it's fine. You still have time.
Okay.
This was when you compared the two different approaches of communicating the uncertain forecast.
Yes.
Anders, you can maybe escape from the presentation, and you can easily go back in time.
Okay. Don't dare to, because I'm afraid of losing the whole.
No, you're fine. Yeah. Okay.
Yep. But now I'm number 12. So it's this one.
Yeah.
Yes.
Concerning southern Sweden. Yeah.
Yeah.
So I was wondering if the two different approaches would be based on different kind of data. Why would the meteorological forecast propose the different focus areas at the beginning if they had the uncertain information? And I assume it's because they were totally convinced that the focus would be shifting, whereas the hydrological kind of forecast must have had some kind of other information, maybe not having weights on the different areas. Can you elaborate a little bit on that?
Well, I would not, because that would imply a sort of a criticism to my methodological community, which I have been teaching for 25 years at the European Center that they should not overinterpret any NWP, in particular not the nice products coming out from ECNWF.
Mm-hmm.
But there is unfortunately a tendency among meteorologists to do that.
Mm-hmm.
And why, I don't know. It might be that it's more convenient. When they are right, they can take the credit. When it's wrong, they are happily blaming the computer for misleading them.
Mm-hmm.
Because I have seen this for long times before 2004 and long times after 2004. And what you see on most of the webs presenting this over-detailed forecast is just a slavish interpretation of the last deterministic forecast from ECNWF or from America or perhaps from the Met Office.
Mm-hmm.
So it's a general disease in the meteorological community. However, the hydrologist knew, as everybody did, that 4-day forecasts of extreme event in 2004 were not perfect. So if it had any meaning, it meant that somewhere in southern Scandinavia there would be a chance of 30 millimeter.
Yeah, yes, but then the question is how to estimate the large circle based on the same kind of data. If you look at the hydrological forecast, you see my point?
Yes, I see your point, and they were in discussion with the meteorologist because they have a daily conference with the meteorologist. They obviously were told that there is some uncertainty, which was not reflected in the methodological forecast, but the hydrological forecast took this uncertainty at heart and avoided to be too specific. And of course, they were making forecasts for Sweden. So if Sweden had been a larger country, perhaps the circle would have been larger. So I can't promise that. But the attitude they displayed was exactly what I had been teaching my colleagues for 20 years at that time. But to my surprise, the hydrologists had never heard me teaching because they were not on the courses. They have found out this just by themselves. And also, you don't need to be a rocket scientist to understand that 4-day forecasts of extreme events are not perfect. At best, they foretold that something of this kind will happen in the neighborhood. So in that sense, the hydrologists were just acting normally, and I can't still understand why the meteorologists then and later on tend to overinterpret all the wonderful details in the NWP.
Okay, thank you very much.
Okay, thank you very much, everyone. I think that's what we have time for today. So again, thank you for listening, and thank you, Anders, for giving the talk. And we will post it as well on YouTube, so if you want to go back and go over it again, you'll have a chance to do that. Okay, thank you very much. Then I will end this meeting.